Hello, this is my 158th problem-solving video on financial math for Actuarial Exam 2. It's mid-October in 2018 here. It's about a month and a half since I made my last video. I'm sorry about that. The fall semester here at Bethel University has been going on and I've been really busy. My hope is that I can continue making at least one, maybe two of these videos per week for the rest of the semester. Actually, in the spring of 2019, I've got good news. I'll be on sabbatical, and that should give me some more time to continue making videos on financial math. And I also want to start making videos on probability to help you study for exam P. So we're looking at problem 7.1.8, a modified version of it from Broverman. It's a difficult subject. We're talking about duration. We've been talking about Macaulay duration so far. We're also going to try to introduce the idea of immunization in this video. And it's not really in the main context of the reading, but it's in this context that for this particular problem, the idea being that we want to immunize ourselves, cushion ourselves against changes in interest rate, try to figure out how to take advantage of changes in interest rates. That's sort of the big idea behind immunization. So that will be introduced in this video as well. It's part B that's really the only thing that you'll see in Broverman's book in the problem description, so I've added parts A and C here. But to do part B, we need to talk about a new concept, something called the modified duration, and we need to relate it to the Macaulay duration to help us do part B. We are going to be thinking about this in a different context. So far we've been talking about Macaulay duration mostly for bonds, but in this context we're going to talk about loans, and you're going to also want to think about this in terms of the lender. The bank is investing in you. They're the lender, they are the investor. We want to look at this from their perspective. What happens if interest rates change and how can they position themselves to take advantage of that? That's sort of the main financial thing you want to be thinking about in all the details. And again, the details are going to be pretty hard. You're going to want to have paper and calculator out to pause the video and check my calculations and really think about what I say. You can see the description of part B is very difficult to understand. It's easier to understand if we actually look at the equation for it, so we'll come to that in a minute here. And again, in part C, we want to give a graphical and financial interpretations. Alright, so here in black you can see this is the actual problem statement. Alright, so take a breath. We got a cash flow series with payments K1 through Kn made at times 1 through n. And this function right here, which is a function of the interest rate, represents the present value at time 0 of this sequence of payments. Okay, so this is a function of I, and when you think about that, right away you should say, okay, that's a function of I that probably decreases, right? As the interest rate goes up, the present value goes down. It's a decreasing function of I. We're also going to suppose, though, in the problem, that I sub 0 is a fixed interest rate at which the loan, if you want to think of it as a loan, as we will in part C, is valued. So let's go ahead and look at part C right away here. It's an interest rate per payment period, which is going to be per month, at which the cash flow series is currently valued. So look at part C. We're going to be thinking about a 4-year loan, which would be like for a car. There's a nominal annual interest rate of 6%. That's just something I'm making up here. And it's going to be compounded monthly, so the effective monthly interest rate is going to be 0.005, 0.06 divided by 12, 1/2 of 1%. And the loan amount is going to be $10,000, so I'm picking, instead of picking the cash flow here, I'm thinking of the loan as the way you usually figure it out. You'd say, I know what I want the loan to be, now what will the monthly payment be? It'll be $234.85, so you're probably going to want to write that information down here, because we're going to need it later on. But now we're going to turn it around and say, ultimately here, pretend this $234.85 at the end of every month for 48 months is the cash flow. And we also want to think about what would the present value of that cash flow be at different interest rates. Let I be a variable, though I sub 0 is fixed. That's the 0.005. Part B is the thing that you actually see in Broverman's book. And in Broverman's book, he writes it as show this derivative equals 0, okay, which is confusing because it makes you think that L is a constant. But no, L is a function of I. And so when you take this derivative, you really need the product rule, okay? Actually, the derivative calculation with the product rule that we're going to do in this video is very similar to a calculation you'll find in the reading in Broverman. It's pretty much the same kind of calculation, okay? So we're really just sort of redoing that calculation, but we want to understand what it means. Evidently, if this derivative evaluated at the fixed interest rate is 0, where this is the Macaulay duration at that fixed interest rate for the power, this is a fixed number here, that must mean if we graph this as a function of I, that the tangent line would have a slope of 0 at this number I0. Probably that means it's either a maximum or a minimum there for this function. Actually, it's going to be a minimum. Before we do the problem, we should take a brief amount of time to notice the relationship between what you see here and what's in blue. We are showing that the rate of change, the derivative, of the present value of the payment stream as a function of I, the interest rate I, accumulated forward. We're taking L of I and accumulating it forward in time by the Macaulay duration, which would be in months for the example. That derivative with respect to the interest rate evaluated at I0, the present interest rate, equals 0. That's a mouthful to say verbally, but symbolically it's not too hard. You should focus on it this way, actually, this last bit here, which it's not letting me highlight just that. Okay, there we go. All right, now take another breath. Let's get into the solving the problem now. So first we are introducing the modified duration. So again, L of I is the present value of the payment stream. You know, in the reading usually it's written P of I. P of I can stand for present value. You could also think of it as a price if it were a bond. Calling it L of I for this problem because we're thinking of it as a loan. Define, first of all, the modified duration. Here's how you do it. You can find this in the reading. The modified duration is this function of I. Take the derivative with respect to I of L of I, divide it by L of I. That ratio would be then the relative percent rate of change of L of I. But because this derivative will be negative, it's a good idea to put a negative sign in front of it to make this whole modified duration positive. Okay? So this, as a positive quantity, is measuring the relative rate of decay of L of I. Okay? We now want to relate this to the Macaulay duration. The Macaulay duration, as we've talked about, is kind of an average time of payment, a weighted average where the weights are the present values of the various payments. So this modified duration must be measuring something similar, an average time of payments. And it is related to the Macaulay duration. The ultimate answer is that the modified duration is the Macaulay duration divided by 1 plus I. How do you see that? Let's take this derivative first. In this formula, kt and t are constants, I is the variable. So this is a power function of I. The negative t needs to come down in front and subtract 1 from the exponent, which is what you see here, negative t there. Subtract 1 from the exponent. It's a sum of those things, so the derivative of a sum is still the sum of the derivatives, so we keep the summation sign there. Then it's a little bit of algebra. We can factor the minus sign out. We can also factor a 1 plus I to the negative 1 out. Here you see the negative sign. 1 plus I to the negative 1 is the same as dividing by 1 plus I. Now use this definition, the modified duration, the negative signs cancel. We also leave the 1 plus I in the denominator. The L of I equals this thing. And then you say, hey, I recognize that this divided by this, that is the Macaulay duration. And there you have it. The modified duration is the Macaulay duration divided by 1 plus I. Okay, so in the usual case where I is positive, the modified duration is going to be a little bit smaller than the Macaulay duration. I'm about to show you that you can simplify these functions for this particular loan example. The details of the calculations are certainly something you can pause the video and check, but I will say it's not the most important thing out of this video. Okay, so here are those calculations for the loan example that we're talking about. With the 48-month payback at the end of every month for 48 months, these $234.85. This is L of I. This is the Macaulay duration. This is the modified duration. And based on the formulas for your basic annuity immediate and basic increasing annuity immediate, you can simplify those formulas, and here they are. Okay, formulas in and of themselves are not so important. It's more important that you understand how to derive them if you need to. And also, as I'm about to show you here in this Mathematica notebook, we can graph these things. Here are the graphs. And we should take a minute here to understand them. The black dots represent the given situation. $10,000 loan, L of I is the present value, $10,000. Every month, again, the payments are every month, at the end of every month for 48 months at a 1/2 of 1% interest rate per month. So you see the 0.005 down here. And based on that income stream for the investor, which is the bank, $234.85 every month for 48 months at the end of those months. If the interest rate were higher, the present value of that payment stream would be lower. And if the interest rate were lower, the present value would be higher. That's why this is a decreasing function. Over here, on the right, you see the Macaulay duration in red, the modified duration, this new concept, in blue. You can see the modified duration is lower because you're dividing the Macaulay duration by 1 plus I. Excuse me. The black dots are the given situation, 1/2 of 1% interest rate per month. These durations are both between 23 and 24 for the given situation. If the interest rate were higher based on that payment stream, that would mean, as we've seen before, that the durations go down. These are decreasing functions as well. And Mathematica can find these values, and yeah, this should be rounded to 10,000. Okay? So that is the given situation. But what we need this for, this modified duration, is to help us do part B now, and also for some future videos we'll look more at modified duration. Let's move on to part B now, which is the main thing in Broverman. So here we are. Let's make it bigger again. So we want to verify this fact right here. We've got a product of two functions. L of I is the first function. 1 plus I to this fixed number, the Macaulay duration evaluated at I0, the given interest rate for the given loan. That's the second function. We need the product rule to differentiate. And again, this follows a derivation that's in the book. So we have the derivative of the first function, L prime of I, times the second function, plus the first function. Then we want to multiply times the derivative of the second, but again, the power is constant because we have an I0 there. This variable is right here. We need the power rule. We bring down the power. We subtract 1 from it. Okay? So this is in symbolic form the derivative, but now we use the modified duration, the fact that it equals this. In this equation we can solve for this derivative, multiplying both sides by L of I and also by -1 to get this. And we can make that replacement. In this formula up here, we can replace the L prime of I with what you see here. And that's what I did right here. So you get this derivative. But now we want to substitute in, which can be rewritten like this. So like that can be simplified by this 1 plus I can be absorbed into here by subtracting 1 from this exponent, which is what you see here. Let's make this smaller again. And now we substitute in I0. And once you've substituted in I0, this term and this term are the exact same thing. We're subtracting them, so we get 0. Okay? So that's symbolic, a purely symbolic thing. The key thing in doing it on your own is just not making a mistake. You got to really think carefully about it. But now, most importantly, we're on to the graphical and financial interpretations of this, of the fact proved in part B. Okay? So this is more important, you might say, ultimately. Let's start by financially interpreting this function. This is a function of I. I'm calling it A of I here, and I could graph it. What does it represent? It takes the present value, L of I, of the series of cash flows at an arbitrary periodic interest rate I, finds its accumulated value at the interest rate I forward in time by the Macaulay duration number of periods where I0 was the current periodic interest rate at which the cash flow series was valued at. Okay, remember the goal. You are the bank, effectively, or you're the president of the bank. You've made this loan out to this person so they can buy a car. Okay, at I0 was 0.5% per month. Maybe right after they sign the contract, something happens in the world, some big, stock market crashes, or something bad happens, or something good happens, and that has financial repercussions and causes going interest rates for these kinds of 4-year loans on cars to change relatively dramatically, maybe over the course of minutes. Based on that, you may, as an investor, having loaned money to this person to buy the car, and they're going to pay you back at the end of every month for 48 months, you may want to resell the loan to a different investor. So you'd sell that series of payments to this different investor, some other bank maybe, and they'd pay you money, and maybe you want to loan that money out to somebody else. You might think, especially if it were a higher interest rate, if the interest rates went up, you may want to reloan it out to somebody else. But the interest rates could go up or down. Is there something you can do to immunize yourself, to cushion yourself in either case? Okay, and ultimately the answer we're going to see is yes. Okay, and thinking about this function is the key to helping you understand what to do. Excuse me. All right, so here we are in the example, for the loan example that we have. What is A of I? Again, Macaulay duration, we found that to be 23.5437 here. And the loan amount, or the payments, were $234.85. So what do we have here? We have L of I, that present value is a function of I, for this series of payments, which you're contractually obligated, even if the interest rates change, to take this series of payments from the person you gave the loan to. That's L of I right there, times 1 plus I to the 23.5437 power. That's the Macaulay duration of that series of payments based on interest rate 0.5% per month. Okay, so this is A of I in this situation, and by multiplying this thing through the top of this fraction, you can rewrite the function this way if you like. Okay, right there. Evidently, based on part B, if you graph this function, it's going to have a critical point at 0.005, and it's going to turn out to be a minimum, we will see. Okay, if you plug in 0.005 into this, you get about $11,246. So that would be, you could say, the current accumulated value of the loan at the interest rate 0.5% by the current Macaulay duration amount of time, the 23.5437 months in this case, almost 2 years. Here's the formula, and Mathematica is writing it in a different way, but more importantly, we can graph this. Here's our graphical interpretation. We see that in fact at I equals 0.005, A of I does indeed have a minimum. So this present value L of I, forward in time by Macaulay duration number of periods, where I0 is the current periodic interest rate at which it was valued at, based on their $10,000 loan, got a minimum at 0.005. At other interest rates, A of I has other values that time in the future. Okay? So, what does this mean? Okay, there's the graphical meaning. It's got a minimum. Clearly, we see the graph that A of I is minimized at 0.005, which is consistent. We've got a critical point with the fact from part B that this derivative is equal to 0. But what does this mean? What's the financial interpretation of it? Okay, this is the most important part. Right? Take a breath. Be ready to write this down, or write down what I say to understand it. Based on the currently computed monthly payments of $234.85, this graph being have a minimum there means if I changes even a little bit away from 0.005, then A of I will increase. Right? You can see it in the graph. It's higher. It's lowest at 0.005. It's higher otherwise. So once these monthly payments have been set, the cash flow has been fixed by them signing the papers. If I changes the future value of the set payment stream, Macaulay duration periods in the future will increase from 11,246 to some higher amount. Is this good or bad from the lender's and investor's perspective? It is good, at least if you're wise about how you think about it, okay? It means the lender, the investor, the bank, is immunized against immediate changes in the interest rate. Take a couple examples. Suppose that right after the $10,000 loan is made, the interest rate per period suddenly jumps. Instead of 0.5%, it's 0.6%. Okay? Not much over a month. It would be a bigger change over a year. At this interest rate, based on the series of 48 payments of $234.85, the lender should have only loaned a smaller amount, right? It's a higher interest rate, so the present value of that series of payments is lower. $9,769.50 instead of $10,000. This amount becomes the new value here, even if it's just an hour later, that the lender could now resell it at. Okay, so by the interest rate going up, the value of that payment stream has gone down. Okay, so that sounds bad. However, after 23.5437 periods, months, this amount will grow in value at the new interest rate, which is higher, to an amount, well, a little bit higher than this one, $1 higher. Okay? Not much higher, but definitely higher. Therefore, if this lender can make an agreement to resell the loan immediately for this lower amount, it's like they're taking a loss right away, but then immediately reinvest the money at this new higher interest rate per period, maybe by loaning it out to some other customer at the new higher rate, there's going to be a net gain in value in their investment of about $1 after about 24 months. And a higher gain if you can even wait longer, 25 or 26 or 27 months, or maybe 48 months, okay? They're still going to come out ahead if they can wait longer. On the other hand, suppose that right after the $10,000 loan is made, the interest rate per period goes down, suddenly decreases to 0.4% per month. At this interest rate, the value of the payment stream is now higher, $10,238.10. This now becomes, if the interest rate goes down, the new value of the loan the lender could resell it at. And they could, this seems better, they could resell it for that higher amount and immediately make a $238.10 profit, so to speak. Okay? So it's good in that way. However, they also could reinvest it at the lower interest rate, 0.4% per month, and still make money, still come out ahead, certainly after the Macaulay duration number of periods, 23.5437 months, and once again you're about $1 ahead, $11,247 compared to $11,246. Therefore, if they resell it and reinvest even at 0.4% per period, even at this lower interest rate, there'll still be a net gain even after the Macaulay duration number of periods, and there would be a bigger net gain after fewer periods, and in fact, the biggest net gain is right away. You might want to just take the money and run, so to speak. But maybe you could find an interest rate higher than this. Maybe it's not loaning it out to somebody else, maybe it's something else, some other investment. Okay? Just make sure you recoup those gains in fewer periods than the Macaulay duration. All right, we're almost done. In summary then, given an investment and in an income stream with a given rate of return, you can immunize yourself against immediate interest rate changes as follows. And I emphasize immediate because, if you wait too long, more than a month, then the payment stream is different. You're not getting as many payments, 47 payments compared to 48, for example. As follows. If the interest rate increases, you can immediately resell the income stream at a lower price than you paid for it, and you'll come out ahead if you invest this money at the new higher interest rate, as long as you invest it long enough, even though you took an initial loss. invest it for an amount of time greater than or equal to the Macaulay duration, and maybe even a little less, since you've got some cushion there. But for sure, Macaulay duration or longer, you'll come out ahead. On the other hand, if the interest rate decreases, if you immediately resell the income stream at a higher price than you paid for it, you're going to come out ahead immediately, certainly. And also, if you reinvested the money, even at the lower interest rate, you're going to come out ahead as long as you invest for an amount of time less than or equal to the Macaulay duration. Okay? So lots of subtle things going on there. As usual, I hope you got a lot out of it. Thanks for watching.